The processor operates on different types of data. These include integers, floating point numbers, texts, structures, and even single bits. All this data is stored in the memory as a single byte or multiple bytes. Let's start with integers, which can be 8, 16, 32, or 64 bits long. If the encoded number is unsigned, it is stored in the natural binary representation, while if the value is signed, the representation is 2's complement. A natural binary number range starts with 0. Such a number contains all bits equal to 0. While it contains all bits equals to 1, the value can be calculated with the expression shown, where n is the number of bits in a number. In 2's complement representation, the most significant bit represents the sign of a number. 0 means a non-negative value, and 1 represents a negative value. For example, with 8 bits, the natural binary range starts with 0 and ends with 255. Signed number starts with minus 228 and ends with 127. Integer calculations do not always cover all mathematical requirements of the algorithm. To represent real numbers, the floating point encoding is used. A floating point is the representation of the value, where here named A, which is composed of 3 fields. First is a sign bit, second is exponent E, and the third is mantis M, sometimes called significant. The value of a real number A can be calculated with the formula shown in the picture, as the multiplication of mantissa, MA, times 2 to the power of exponent EA. There are 2 main types of floating point numbers, single and double precision. The first is a number which is encoded in 32 bits. In C, it is a float data type. Double precision floating point number is encoded with 64 bits. In C, it is a double data type. The real numbers representation in computers is standardized in the document III Standard 754. There are 2 features implemented which makes the calculation easier for computers: the bias exponent and the normalized mantissa. A biased exponent means that the bias value is added to the real exponent value. This results in all positive exponent, which makes it easier to compare numbers. The normalized mantissa is adjusted to have only 1 bit of the value 1 to the left of the decimal. It requires an appropriate exponent adjustment. Texts are represented as a series of characters. In modern operating system, texts are encoded using 2-byte Unicode, which is capable of encoding not only 26 basic letters, but also language-specific characters of many different languages. In simpler computers, like in embedded systems, the 8-bit ASCII code is often used. Every byte of the text representation in the memory contains a single ASCII code of the character. It is common in assembler programs to use the 0 value as the end character of the string, similar to the C or C++ null-terminated string convention. Data encoded in memory must be compatible with the processor. Memory is usually organized as a sequence of bytes, which means that every byte can be individually addressed. For processors of the class higher than 8-bit, there appears to be an issue with the byte order in longer data types. There are 2 possibilities. Little-endian. The low-order byte is stored at the lower address in the memory. And the big-endian. The high-order byte is stored at the lower address in the memory. For example, In a 32-bit class processor, the little-endian double word starting at address 600 has the lower byte at this address, mid-lower byte at address 601, mid-higher byte at address 602, and the higher byte at address 603. In big-endian order, bytes are reversed, so at the starting address 600, the higher byte is stored.